Welcome back, and let us resume our discussion on the stability analysis for the common mode feedback loop for our Cascode amplifier. And we are looking into the parasitic capacitances that are going to determine the overall capacitance at the non-dominant pole, and we are looking at the condition where we are trying to make the dominant pole at the output GMRO times the non-dominant pole, so that a good phase margin close to 45 degree can be achieved. And towards that end, we will, the target is that the overall capacitance over here, the compensation capacitance or the load capacitance that we are adding, or which is coming by itself because of the next loading stage, that is at least around GMRO times the net parasitic capacitance over here. And therefore, if the capacitance over here becomes too large because of other design constraints, the compensation capacitors to be added can become large, and therefore we are just trying to see identify the different components of the capacitances that are going to come in, and from there we will go to some other analysis like the noise analysis, which will enforce certain sizing constraint for some of these devices. And there also we would like to make sure that those sizing constraints are not enforcing very large capacitance at this particular node. So, this is something we would like to make sure for the common mode overall common mode response. Now, these are the capacitances we have drawn, and as I mentioned, I am ignoring the source to substrate and drain to substrate capacitances, assuming them to be relatively small, and they also do not contribute to the Miller multiplication, because they are also is going to appear between source and AC ground, because assuming that all the body terminal for the PMOS and NMOS are at either VDD or ground respectively. So, they are the CSB and CDB component of all the MOSFETs come between the drain and the ground. Therefore, they are not Miller multiplied, and their values are also significantly smaller than the CGD component, which is in turn smaller than the CGS component. Therefore, we are ignoring the CDB and CSB. So, in summary, these are the capacitances that we have. Remember that we decided to use a diode connected load for the error amplifier. So, both of them are having low impedance node over here, impedance given by 1 upon GM approximately for these two transistors. And therefore, if I look at the overall capacitance, so we had the CGD of M1, the gate is AC ground, therefore, it appears directly between the drain and AC ground, not having Miller multiplication. CGS of 4, which is going to be significantly larger than CGD values over here. Now, if I look at the CG D5, that is also appearing between this point and the gate of the M5, and again at this point if I look at reverse Miller multiplication factor, that is not going to be significant for CGD5, because it is going to appear as 1 minus 1 upon A. Gain from this to this point is large, but the Miller multiplication from here to here is going to be going to include the reverse gain 1 upon A. Therefore, this is also not going to contribute heavily. Therefore, the dominant capacitances that we have over here is going to be CGS at this particular node. The dominant capacitance that we are going to have is CGS4, CGD5 and CGD1, and among these capacitance at the P2 pole, we can see that the CGS4 can be the larger one, CGD5 and CGD1 can be relatively smaller. Both of them are coming as it is close to CGD1 only, therefore, they are contributing smaller factors. So, here I would like to make sure that whatever sizing constraint we are going to have, they do not increase CGS4 too much, and for that we also should remember that what is the dependency on CGS4 and device dimension. So, if I am looking at this node, the CGS4 depends upon W as well as L. Remember, the origin of CGS4 depends upon the oxide capacitance, and therefore, the area of the total gate that you have for the MOSFET. Therefore, larger W and L for this device can induce larger CGS4. So, we would like to keep the W and L of this device relatively small. We do not like to size this too large, otherwise it will introduce larger CGS4. As long as the other capacitances are concerned, CGD1 and CGD5, they are relatively small, and we will see that the sizing constraint for the M5 and M1 should be such that they do not enforce very large CGD. Now, what does CGD depend upon? CGD1 and CGD5. So, once again, if I remember the dependency from the device structure, the CGD is going to have two major components. One comes because of the overlap of the gate dielectric and the drain region. So, you are having overlap capacitance. If I am, let me forgive me for the bad drawing. So, you have an overlap region between the gate dielectric and the drain, which leads to an effective overlap length L overlap, and that also leads to a effective capacitance between the gate and the drain region, likewise gate and the source region. Because what is happening, because when you are putting some more charges on the gate, the region just below the overlap is attracting more electrons, and therefore, some charge on the gate is balanced by the electrons getting attracted in the n plus region, where the gate is overlapping with the n plus. So, that leads to a fixed CGD component coming from C overlap. So, that C overlap component is present on both sides, and for saturation region the CGD is dominated by C overlap, and we know that the channel in the saturation region is skewed towards the source side, and the drain side you do not have much of the channel charge coming. Therefore, if you change the VGS, the channel charge is mostly controlled by VGS and a much lesser extent by the VGD. Therefore, the CGD does not play a significant role in changing the channel charge and saturation. Therefore, the gate capacitance, which is determined by the COX, that is mostly ascribed to the source to gate capacitance. So, in the saturation region, the CGS is accounted by mostly the gate oxide capacitance COX times W times L. So, that becomes proportional to the gate capacitance. On the source side also you have overlap. So, the C overlap part is also there on the source side, but in general the oxide capacitance is significantly larger. Therefore, in saturation region CGS is some constant factor smaller than 1 times COX times W times L plus C overlap, whereas the CGD is approximately equal to C overlap only, because CGD side you do not have much control of the gate to drain potential on the channel charge. So, the effective capacitance for the gate to drain junction arises because of the C overlap in the saturation region. And C overlap, if I look at the geometry of the device, the C overlap would depend upon the overall area of the overlap between the gate and the drain region. So, if this is the L overlap that I am drawing, L overlap showing the slight overlap between the gate dielectric and the n plus region, the overall C overlap will depend upon this L overlap times the total W of the device, right. L overlap is the technology parameter, that is feature of the technology, does not change from device to device. What changes is the W. So, this direction is the W of the device. I am drawing the 3D projection. So, you have n plus, this is the channel, and you have this is the gate, and this way you have the W. This is the total W of the device. This region I am calling this as L overlap. So, this is L overlap, and therefore, the CGD will be determined by the W of the device. If you are increasing the W of the device, the CGD of these MOSFETs, the M1 and M5 pair will also go up increasing, and as a result it will push this pole towards lower frequency. So, I would not like to have large W for this device, neither I would like to have large W for this device. Likewise, I would also like to avoid large L and WL product for this device. So, this is something we should keep in mind while looking at the sizing of the cascode. If I look at the consideration that we are already aware of, for example, if we want to have a good gain, for a good gain from the cascode amplifier, I would like to have the GM RO product to be large. For that, I would like the W by L of the input pair over here to be large. So, that is again conflicting. So, you are having if you want to have larger gain for a given current, you would like to make the W by L of this MOSFET large, but if you rely on the increase in W, then the CGD is not strongly affected by the W that is coming the CGD is getting strongly affected by the W, and therefore, that is once again getting increasing the overall node capacitances over here. So, when you are trying to increase the gain by increasing the GM of the input device and hence the W of the input device, we can see that the overall CGD1 is going to dominate, and this node can be ascribed, or the total capacitance over here can be ascribed to CGD1, whereas the other capacitances do not contribute, or the W of the M5 does not contribute to the gain so much. So, here the W can be reduced significantly, and we will see that the noise constraint also forces us to have a larger L for this device and poorer GM for this device, and therefore, the CGD over here may not be an important constraint. Likewise, if you are looking for the other Cascode device over here, the CGS, it depends upon L as well as W. If you want good RO and overall good gain over here, which is dependent upon GM RO square, that depends upon two factors, once again bias current and L, and if you want to have good gain, one option is to reduce the bias current, and there you do not rely so much on L, and in that case we can rely on increasing the or having a nominal W by L of this device by reducing the bias current, so that the CGS4 over here also may not be very dominant. So, however, the CGS4 is having a value which is larger than CGD1. So, these are the two which are going to dominate. The CGD5 may not dominate so much, because here we will see that the major factor that comes in CGD5 or M5 is basically the channel length. You need to have a larger channel length. You can sacrifice the W of this device. So, this CGD does not matter so much. CGD1 is a major factor. Likewise, for this device, the W by L may not matter too much. The Cascode device we will see very shortly also does not play a very important role in determining the noise of the Cascode configuration. Therefore, for the Cascode device, once again the GM does not play a very important role, and we can afford to sacrifice the GM of this device significantly by reducing the W of this device significantly. So, if you want good gain, L can still be kept large, say 2 micrometer, whereas W can be reduced so that the CGS4 is within limit, because it does not, the gain does not depend upon GM of this device, it just depend upon the RO of this device. So, by taking appropriate design decisions, I can try to minimize this combination of these three capacitances, so that they do not interfere with my dominant pole compensation. So, the summary out of this is we just identified that at this second pole over here, what are the capacitances coming in, then we looked at the dependency on the dimensions, and then we are also trying to see that following other design constraints, when we are trying to size different transistors, how those sizing issues are going to affect the total capacitance over here. The worst case situation is because of this M1, because here I do need a good W by L and hence good GM, and that is going to increase the CGD1. So, that becomes the dominant factor, that is becoming the dominant conflicting factor for the minimization of C at this point. Other two may not be so critical, because the sizing of these two are favorable to reducing the CGS4 and CGD, because first we will see that the W and L of M4, the product can be minimized, can be reduced, because the overall W by L does not matter for this device in the overall gain expression, because GM of this device is not coming into picture. So, I can afford to have smaller W by L, and despite having a larger L, I can reduce W, so that the overall product CGS4 is within limit, it is smaller. That is one thing, and likewise the W by L of M5 also does not play any significant role in determining the gain. Therefore, I can significantly reduce the W by L of M5 without affecting the gain over here. That is another point. And another sizing constraint for M5 will come from noise, where I am telling you ahead of time it will require larger L or poorer W by L. So, here even if we have larger L for M5, it does not degrade the CGD so much, because it is dependent upon W and not upon L. So, we should be able to identify that, okay, if your other constraints coming into picture for sizing, which constraint is conflicting with the stability requirement or compensation requirement. Here the major sizing constraint which is conflicting with the stability requirement is the gain factor, where I would like to have larger GM for this, larger W for this. Other wise, these two transistors and their sizing constraint coming from noise, coming from gain, they are not conflicting with our compensation requirement. So, it serves to have a better idea of the device structure, so that we can think about which device is contributing to the dominant non-dominant pole over here, so that we can judiciously choose the sizing of the other devices while satisfying multiple criteria, say the compensation and the noise together. Another very important factor that we have to also see is the swing. Now, if we afford to reduce the W by L of these devices, as we just discussed, what is going to be affected negatively is the swing, because once again, if the W by L of these devices is reduced, we know that overdrive voltage for a given bias current will be increased, and then using our bias scheme, we know that the maximum potential that you can have over here is VDD minus 2 V overdrive, and if you increase the V overdrive by reducing W by L, swing will be hampered. So, while you try to achieve or improve one metric, the other metric get jeopardized. So, in general, that trade off is always there, and you have to make a proper choice. You have to arrive at the sweet spot, which is basically catering to the set of specifications you are trying to implement. And as far as this node is concerned, anyway, we have seen that the node capacitance, node impedance is low, and therefore, even if you look at all the other capacitances coming into picture, even if it is having a Miller multiplication for CGD5 at this point, because of the impedance being low, it is not going to affect much. But only thing is, we have to be careful that if we try to make the bias current of this stage too small to save power, once again the GM over here can get reduced, and it can become very small, 10 to the power of minus 5, 10 to the power of minus 6, and in that case the R over here can become, the overall impedance over here can become significant. So, if you are trying to save the bias current in this stage by reducing it aggressively, the overall small signal resistance over here will become maybe close to RO, because if you are in subthreshold regime, transistors are having very small current, microampere or close to that, the GM can be pretty poor, especially if you, on the top of that, if you choose a poor W by L for this, and in that case the overall small signal resistance over here can increase, and then you also have this Miller multiplication for CGD5 coming. Those things can complicate the stability issue a little bit. So, you have to be aware that, you know, whatever design choice you make at one point, for example, for reducing the bias current over here, that can also influence your overall stability, because here also again it can bring up a non-dominant pole, which is probably even lower frequency than this one, because it is having a Miller multiplication factor of the CGD5. Along with that impedance over here, which is getting closer to RO, GM is no longer, or 1 upon GM is no longer much smaller than RO, as we always assume. So, that will push this node even lower than this one, and that will start contributing as a dominant pole. So, rather than this being the non-dominant pole, this will become the non-dominant pole, and it will create problem with the phase margin. So, although for overall analysis we ignore this pole, but for our particular application, if we are looking at low bias current, we have to be careful that this does not become the non-dominant pole, otherwise it will fight with this one, or it can become lower than this one, and then interfere with our compensation we are trying to achieve with the help of a compensation capacitor over here. So, that will mandate that, okay, then you add another capacitance over here, and then try to compensate this one as well as this one, so that this does not become the non-dominant pole, this stays the non-dominant pole, this stays the dominant pole, and this is significantly lower. So, all those constraints we can definitely look in simulations and observe the phase margin coming up. Okay. So, before we go further, any question on, you know, whatever point we discussed. So, we have discussed a very high level that, okay, what is the overall compensation scheme, and what are the issues which are going to complicate that compensation scheme. So, we are at the high level, we are starting with a relatively easier compensation scheme, which is dominant pole compensation. But I just tried to mention that what are the issues which can complicate it further. If you want to have a good dominant pole compensation, the sizing constraint of this transistor must be taken care of. You should not make this capacitance too large, otherwise it will require much larger cap over here. And the second thing that I discussed is that you should not make end up making this one the non-dominant pole. This pole should not end up being lower than this one, otherwise you will have to compensate this one also separately by putting even larger cap over here, and then it can So, any other issue? We will see that, okay, means if you want to compensate the common mode loop, right now we are constrained with the single loop, and we the same CC over here or same CL over here is good enough for compensating both. But in some applications you may have to keep the bandwidth of the common mode feedback loop much lower than the differential. In that case more complications arise, and we can look into schemes where these two can be compensated separately. Alright, so let us look into the noise analysis for Cascode amplifier and try to arrive at the overall input referred noise and try to see the sizing constraint provided by the noise. So, for noise analysis also I can basically go ahead with the differential half circuit. So, ultimately we are going to look at the two output nodes separately because they are going to have uncorrelated noise. I can look at the differential half circuit and look at the contribution of each of these transistors. We have to remember that the gate potentials of the other 4 transistors are anyway constant, so they are DC bias points, and we have to apply the MOSFET noise, that is a flicker noise at the gate, and the channel current noise in parallel with the channel current source of the MOSFET, and then arrive at the final output noise expression divided by the overall amplifier of the gain to arrive at the input referred noise at the input point. That is what we are going to do in brief. So, let us do that and confirm the contribution of these transistors in determining the input referred noise. So, the steps are pretty similar to what we have done for the 2-stage already. So, the more crucial ones will be the Cascode one, because we will have to conclude certain things about them. The NMOS and the PMOS connected to the VDD and ground, they are going to be relatively straightforward, as we will see. For the differential half circuit, once again I am putting the source of the input pair to ground, and for the input pair once again I can have the VN G1 square. Likewise, I can just number these. Let me call this 1, and this is your 2, 3, 4, 5. Now, looking at the 5th one and 2nd one and also the 1st one, they are having their sources at AC ground, and therefore, I can easily translate their channel current into an equivalent gate voltage. So, if I model their channel current I in CH5, and likewise I can model this as I n CH2, likewise I have I n CH1. So, these are the thermal noise current associated with the channel current for the 3 MOSFETs, and their sources are ground, and therefore, I can also convert this channel current into an equivalent voltage at the gate, and the conversion is simple. You just need to divide this channel current value by the GM square, because the equivalent noise voltage VNG square times GM square will result in this equivalent channel current. So, I have 2 sources. Of course, for the flicker noise we anyway represent it with the voltage connected in series with the gate, because the mechanism of flicker noise, it arises because of the interaction between the carriers and the dielectric, and effectively results in an overall wave VT shift between or VT shift for the MOSFET, and that can be modeled as an gate voltage in series with the MOSFET. So, we try to model the flicker noise as a VT shift, right. If you remember our discussion, the basic origin of the flicker noise is that it is arising because of the trapping of charges, which is basically changing the voltage drop across the oxide, and in effect it is changing the required amount of positive gate voltage or positive charge on the gate voltage to balance the equal amount of negative charge in the channel. So, if you are having certain bias current and assuming that the bias current is fixed, and therefore, the charge in the channel is fixed, right. So, assuming that the channel charge is remaining fixed, and on the top of that you have the MOSFET gate where you are putting positive charges, what we have if the channel current is fixed and the bias current is fixed, we assume that this is fixed, and Because of the trapping, however, you are having some additional charges coming in. So, this Q is changing over time. As a result, what we say is the required amount of charge to have the same amount of channel charge over here, the required amount of positive gate charge to have the same amount of channel charge over here also keeps fluctuating. So, what we can say effectively is that the effective VT of the MOSFET is fluctuating, and how do we represent that? By putting a voltage in series with the gate of the MOSFET. That is why this flicker noise comes in series with the gate of the MOSFET, and so you can effectively see is at a noisy VT of the MOSFET, whereas the channel charge comes because of the electrons transiting through the channel and having random fluctuation in the conduction path. So, if I want to translate the gate voltage or the noise voltage into current, that is possible by multiplying it with GM square. Likewise, if I want to convert the channel current into an equivalent gate voltage, and again divide it by GM square, provided the source of the MOSFET is ground, because only in that case I can say that this equivalent VG square, VGS square times GM square would result in such a channel current. So, let us do that. For each of these I can write down the VG1 square as the VNG1 square, which is inherently because of the flicker noise, which is automatically modeled as a voltage source in gate with the in series with the gate of the MOSFET. So, I do not need to do anything for that, but I have the second one, which is INCH1 divided by GM1 square, and I can do this only if the source is grounded, and therefore, I have the VNG1 square, which I can express this as the flicker noise. So, you have K upon W L CO X times F plus I channel upon GM1 square. So, we have 4 KT gamma GM, which is the expression for the channel current noise divided by GM. So, this is the expression for the VG1 square. So, I will just call this the VG1 square, the total VG1 square, which is the VNG1 square because of the flicker noise plus the channel current divided by GM1 square. So, this is I can just denote it like this, and likewise I can do it for others also. I can express the total current, total noise of this MOSFET as VG5 square, and likewise for the 2 I can represent it as VG2 square, as simple as that. And then for each of these I can see that they are acting like the input device of Cascode amplifier. So, if I take M1, this is acting like the input device of the Cascode. If I am calculating the effect of VG1 square, the others will be set to 0, and I will just calculate the output voltage because of the VG1 square, and we know that what is the gain from the input to the output, we have already calculated that. So, we have a 1/3 factor times GM square RO square. So, let us write that down, but we should also be careful about picking the right GM, because ultimately we have to look at the overall input referred noise, and we have to divide it by the overall gain of the circuit, which is GM1 square times RO square. In all these cases, ultimately at the output point we are going to get the RO of this MOSFETs. So, just in order to distinguish that which GM and which RO is going to contribute to noise in which fashion, I would like to preserve the subscript. I should not simply write it down as GM RO whole square. I have to identify which GM and which RO is contributing in what fashion. So, let us preserve the subscripts and calculate the VON square, that is our total output noise because of the VG1 square. That is going to be K upon W L1 times COX times F plus 4 KT gamma upon GM1 times GM1 square times the impedance over here, the overall output impedance that we get because of the M3 and M4. So, that is basically GM3 square, we have to keep the square. So, GM3 RO3 times RO2 square, and we have the factor of 1/3 coming in also, that also we have seen, because the current gets divided, you have RO over here, RO over here, and another RO here. So, that 1/3 factor comes in, and then we have this expression. Now, when we get the input referred noise because of V and G1, we will be dividing it by the same factor. So, this will be divided by the same factor basically. This is VON square divided because of VN G1 square. Likewise, I can write down the VON square output noise voltage because of the VG5 square. Now, for the VG5 square, let me just write it VG5 square times the overall gain from input to the output. Now, once again, if we look at the overall operation, if I am looking at the gate voltage of this one, what is the impedance provided by this? We have just discussed while discussing the common mode response. So, there I will not treat this as AC ground, because if I am looking at the signal over here and putting the signal at the gate of M1 at AC ground, that means both the signals, the input signals at AC ground, and after that we have another current source which is also at AC ground. Therefore, this will represent a stacked NMOS which is having an impedance of GM-RO square. It will not be just RO, it will be GM-RO square now. Therefore, while considering the effect of this VG5, I will ignore this branch, just like we did in the common mode feedback analysis. That distinction you should keep in mind. So, that when we are analyzing the effect of this VG5, we are ignoring this branch. Why? Because the input signal is 0. Therefore, you have stacked transistors, 2 NMOS with gate voltages at AC ground. Therefore, the impedance looking into the drain is GM-RO square. Here it is just RO, and therefore, I can ignore this safely. So, I ignore this, and therefore, this is our simple cascode amplifier with input signal at this PMOS, and therefore, the input signal is VG5 square, and that I have to multiply by the gain of this circuit resulting from this amplifier. And we know that when we calculate the gain of the circuit, we get a 1/2 factor because of the current division at this point, RO up, RO down, or in this case basically RO of this M5 and RO of the remaining circuits, and that multiplied by the overall impedance over here. So, that is again going to be GM3 RO3 RO2 square. So, same factor, and also this whatever 1/3 factor that I have written, that is also going to be 1/3 square, because ultimately we are looking at the current square. So, this is the for the first branch also current square, and therefore, the division factor 1/3 also becomes square. So, I just missed that square for the 1/3. And now, the last one is the VG2. So, VON, so this is because of VG5, and likewise VON square because of VG2. Now, for VG2 the situation is very similar, only thing is we are going to get the impedance looking upward. So, for VG2 the expression for the gain from input to output is same as what we have from the VG5 to output. Only thing is in terms of the MOSFET, the impedance will be contributed by M3, M4 and M5. This node is again not going to contribute much, because when I am analyzing the effect of VG2, once again this MOSFET is going to represent a impedance of GM times RO square, because of the 2 stacked MOSFETs coming into picture. This is not an AC ground for that operation, and therefore, I can once again safely ignore this. Looking at the gate of this M2, I can find out the output voltage over here, which is going to be again 1/2 square times VG2 square times the overall impedance looking up, because remember half of the current goes up and then it gets multiplied by this impedance, which is basically GM4 RO4 times RO5 square. So, this is the overall output voltage because of the contribution of M5, M2 and M1. Now, if I want to look at the input referred noise because of these 3 combinations, I need to divide all these 3 components by GM1 square times the RO3, the basically impedance looking downward from here square. That is the gain from the input to the final output over here. That is what we need to do. And
so in the V out due to VG5, shouldn't there be a GM5 square and like that for GM?
yes, sorry, I missed the GM factor. So, VG5 and GM5 square, yes. yeah. So, ultimately we are looking at the voltage. So, GM5 square, likewise here also GM2 square, GM2 square. Alright. So, now we have the expression for the output voltage in terms of the gate voltages 2, 5 and 3, and all we need to do for getting the input referred noise is divided this factor by GM1 square, GM3, RO2, RO3 square by 1 upon 3 square. This is the gain, and therefore, I can look at the VIN square because of these 3. I have not talked about the other 2, let us discuss that later. First we calculate this, and now if I take the assumption that these are symmetrically biased and the sizes are also symmetric, under that condition I can assume that their ROs are similar just for simplicity. Remember that the bias current in this branch is different, and you may have a bias current over here which is double. So, the RO of this one may be lower, almost half as compared to the RO of this, but just for simplicity, just to keep the numbers simple, I am assuming that these 2 are having similar RO and GM, and these 2 are having similar sizes, these 2 are having similar sizes, and therefore, I can replace the GM4 RO4 RO5 by GM3 RO3 RO2. So, let us do that. So, I have the VN1 square given by the first term, which is V G1 square. This term gets divided as it is. So, you only get the VG1 square, plus you have the second term which is VG5 square divided by this number, and this again gets divided by 1 upon 4. You have VG5 square, and this term goes as it is. You have the 3 square terms coming in. So, you will have the 3 square coming in over here, and you have the GM5 square term coming in, GM5 square. So, and that divides by GM1 square. So, I have just divided this second expression by the gain GM1 square times this number. So, this is the second factor which is coming in, and then I have the third term which is the VG2 square divided by once again the same factor over here. So, I am getting GM2 square divided by GM1 square, and once again this gives me 3 square in the numerator, and you have the 2 square coming in anyway in the denominator, 2 square here. So, that's the input referred noise VIN square because of the 3 components, and once again these are the constant terms. So, they are not going to be very important. The important factors are the dependencies on the GMs of these individual devices. So, here if I look at the dependencies and preserve only the GM terms, I am getting VG1 square plus GM5 upon GM1 square plus GM2 upon GM1 square. And if I look at this ratio, definitely it means that I would like to increase the GM5 upon GM1 ratio. I would like to reduce the GM5 and GM2 as compared to GM1. So, I would like to reduce the GM of 5, I would like to reduce the GM of 2, and I would like to increase the GM of 1 for getting a better noise. And likewise, I have the VG1 square also coming in as it is, and of course, I have to multiply it with the VG5 square and VG2 square respectively. So, of course, they are going to have their own dependencies on the devices, where we can write the entire expression, but at least in terms of GM, what we can see is that definitely increasing the GM1 is going to help us in bringing the noise contribution of these 2 down. If we look at the VG1 square itself, there also we have the dependency on GM1 upon GM1, because you have the channel noise getting divided by GM1, and therefore, you have the overall factor which is proportional to 1 upon GM1. So, now we can elaborate the expressions a little bit more and write down the expression for VG1 square. We have already figured it out over here. So, I can write down the VG1 square, which is K upon W, L, COX and F, and you have the 4 KT upon GM1. This is W by L 1, and likewise you have the second term which is GM5 square upon GM 1 square times the VG5 square, and VG5 square, once again we know the same factors are going to come, therefore K upon W L5 times COX times F, plus you have the 4 KT upon GM5, and likewise you have the third term coming in, GM2 upon GM1 square times Vg2 square, which is also having the same factor, which is K upon WL 2 COXF plus 4 KT upon GM2. So these are the terms that we finally have, and I can once again break this GM also down into their respective expressions and look at the W by L expression or W by L dependencies for all these individual transistors. So for the GM1 it is clear, we have the increasing the W and L1, it seems like it can increase the, or if I increase the W of the input device, it can definitely help me in reducing the 1 upon F noise. Likewise, having a larger GM1 is reducing the thermal noise for the input device. Likewise, if I look at the other two expressions, definitely larger GM is helping us in reducing the overall noise contribution for all other device. So without any doubt, I can definitely say that increasing GM1 is going to help, and the other components over here, GM5 and GM2, also give us hint that yes, reducing GM5, GM2 may be a possible method. However, we are looking at the thermal noise contribution because of GM5 and GM2, they are coming in the denominator, and they can once again, if you keep the GM2 and GM5 too small, they can start dominating. So again, there is a trade-off with the 1 upon F component and the thermal component. Let us break it down further into W by L dependencies, so get more clarity. So GM1 is having root under W by L dependency, and GM5 square, if I just look at the parameters, you are going to have the ID5 and you are going to have the W by L. So if I look at GM5 and GM1, once again their currents are kind of ratioed. So if I can assume that the DC currents in M5 and M1 and entire this stack, they are kind of ratio, they are not independent. So for example, I can keep a total current I over here and I over here. The total current in M5 is going to be sum of these two, and also the current in M5 and M2 are also proportional. So however, if I look at GM5, it may seem that okay, means having an appropriate division of the bias current in these two branches can help. So if I am taking larger fraction of the bias current here in order to increase the GM1, whereas a lower fraction of the bias current coming over here, at least it will reduce the GM of the M2. So we can write down this as W upon L 5 ID 5, and we have the GM1 square, which is W by L 1 times I D 1. Likewise, you have the K upon W by L, W times L 5 COX F plus 4 KT. Here you are going to get root under W by L, so 5 times root under ID 5, I5, whatever I have mentioned. And likewise, in the last term, I have the GM2 upon GM1 ratio. Once again, W by L 2 I2. Let me call this I1 to keep the same notation. I5 means the drain current in M5, I1 means drain current in M1, and I have W by L 1 times I1, and likewise you have the WL 2 COXF KT upon GM2, which is W by L 2 times I2. And so now if I look at the W by L dependencies, I can take this in, and therefore you will have the L square 5 coming over here. So if I take this in, I have L square 5 coming in this term. So I have L 5 square in the denominator, and Here, however, I have once again root under W by L coming into the denominator. So, this gets cancelled with the term, and I have root under W by L 5 coming in the numerator. Likewise, in the denominator expression, I have the W getting cancelled, and this is going to give me 1 upon L2 square in the denominator, and here when you are cancelling this, you are getting the W by L2 term in the numerator. And therefore, increasing the L2 and L5 definitely can help us in minimizing the noise contribution for the noise contribution of the M5 and M2 stacks. So, these two transistors contribution for the overall noise can be suppressed by having a larger channel length for these two devices. And at the same time, if I look at the overall condition for M1, having a larger W for M1 and having a larger bias current for M1 in terms of I1 is going to definitely help us in reducing the noise contribution for the overall amplifier, and likewise it is also going to help us in increasing GM1. So, larger W1 and larger I1 is going to help us in achieving overall lower noise contribution. Likewise, L5 larger, L6 larger is going to help us in reducing the overall noise contribution. And likewise, if we look at the bias current contributions, once again for I2 and I5, we can see if we take I2 and I5 inside, both of them are coming in the numerator in the first one, and in square root or I5 and I2 coming in the second expression. So, they are not trading off that significantly, and they are all proportional to I1. So, if I just keep the ratio of I1 upon I5 and I1 upon I2 upon I5 sufficiently large, that can help us. But you remember that I5 upon I1 ratio is not in our control. So, I5 is anyway going to be greater than I1. I2, if you make the I5 say close to I1, so I5 you make close to I1, allowing a smaller current to flow in I2, then you have this term overall getting reduced. So, what I can try to do is the tail current source I5, I can try to make it I1 plus delta, and this delta if I try to reduce, the delta, that will reduce the I2 and hence I2 upon I1 ratio, and therefore, it will reduce the contribution of this term further. So, having a larger I1, having a smaller delta, which is basically I2, which is determining the I2 upon I1 ratio, can also help in minimizing the overall noise contribution of these transistors. So, we have arrived at the dependency of the overall input referred noise on the bias currents of these devices and also the dimension of these devices. And important takeaways with respect to sizing is a large L5, large L6, a large W1, and significantly strong dependency on the input bias current. So, once again, the bias current of the input stage is going to play an important role, and if you want to especially minimize the 1 upon F noise, 1 upon F noise corner. So, once again for that I will be equating this 1 upon F expression with the remaining white noise expression, and there once again we will see that the I1 will be coming in the numerator. So, if I take away all the 1 upon F expression from this bracket and equate it to the other terms, you will see that I1 will be coming in the numerator, and therefore, in order to reduce the 1 upon F noise, once again I1 is going to play an important role. Likewise, W by L1 is going to play an important role. So, 1 upon F noise corner will be dependent upon I1 and W1 of the input device strongly. And likewise, thermal noise contribution, we can look at the other dependencies, reducing the I2, reducing the GM of M5 and M2 by having a poor W by L or larger L for these devices. That is going to reduce the thermal noise contribution because of these devices. So, this is going to give us some additional design steps, and when we are trying to optimize our folded cascode amplifier to meet overall set of specifications, this is giving me another set of constraints and is going to play an important role in fixing the sizes of input devices as well as the stacked devices in the cascode. So, here you have to go back and look at the constraint that we discussed with respect to stability, that okay, what is happening when you're trying to compensate the loop and which capacitance is dominating, which device is contributing. So once again, from here we can go back and try to check that what happened to that compensation scheme that we discussed. If we go for the noise minimization, whether it is conflicting with my compensation scheme and whether it is increasing the capacitance at the non-dominant pole. And so far, another important point that we have not answered is the contribution of the Cascode devices. These two middle two devices we have not counted, so let us discuss that briefly. Any questions before we proceed? Okay, so we can take a short break and then come back, address the other remaining issue, that is the contribution of the Cascode devices and the other design trade-offs related to the bandwidth and the gain. How do they conflict with the noise requirement?